Hello friends, welcome to this video about propagate, generate and delete in a carry adder. In this video we will explain how, when doing a binary addition, we can take advantage of certain conditions to design improved adder circuits. First, let's consider the full adder function in one stage of a sum, as shown in this full adder. This is the full adder, with the 3 inputs and the 2 outputs. And this is the logic table of an addition of 2 numbers, A and B, with the carry in, the sum and the carry out. Now let's look in detail at this table. We can distinguish 3 situations: carry delete, carry propagate and carry generate. The carry delete scenario is the one delineated in the first square. Note that the output carry is always 0. These are the conditions under which, independently of what is the value of the carry in, the output carry is 0. The carry propagated scenario is the one delineated in the second square. Note that the values of the carry in and the carry out are the same: 0, 1, 0, 1, 0, 1, 0, 1. These are the conditions under which, independently of what is the value of the carry in, the same input carry is propagated to the output. The carry generate scenario is the one delineated in the third square. Note that the carry output is always 1. These are the conditions under which a full adder is generating a carry out equal to 1 independently of the carry coming from the previous stage. So this means that I can now define 3 new logic functions associated respectively to each of these delete, propagate and generate scenarios. From the carry delete scenario, we can say that if A and B are equal to 0, the carry out is 0. From the carry generate scenario, we can say that if A and B are 1, the carry out is 1. And from the carry propagate scenario, we can say that when the carry in is 1 and A is 0 and B is 1, or A is 1 and B is 0, then the carry out is always 1. Converting these scenarios into equations, we have the carry delete scenario is the function A plus B equal to 0. The carry generate scenario is the function A, B equal to 1. And the carry propagate scenario is the function A, B prime, that means A, B prime, plus A prime B equal to 1, which actually is the exclusive OR function of A and B. So, D equal to 0 represents the condition when a carry is deleted. G equal to 1 represents the condition when a carry is generated independently of the value of the carry in. And P equal to 1 represents the condition when an input carry will be propagated to the output carry. So, these are the logic equations representing each of these logic functions. So, I have converted the carry generate scenario, carry propagate scenario and the carry delete scenario into 3 equations: G equal to 1, P equal to 1 and D equal to 0. Now, it is interesting to note that we can combine the G and P functions to produce another expression, which is this one. Which means the carry output is 1 if either the carry 1 is generated or the propagate function is 1 and the input carry is 1. So, if either of these conditions are true, then the output carry will be 1. To see the importance in practice of these functions we have just defined, let's first draw the circuit for the summation using a concatenated chain of full adders in a similar way as we normally do by hand when we make an addition. Technically, this is called the ripple carry adder. Each one of these blocks is a full adder. All I am doing is taking the carry out from each full adder and cascading them to the next full adder. As you see, with this methodology, the constraint is that we have to wait for the successive carries to be generated in series before completing the sum. Now, the carry generate scenario and the carry propagate scenario have given the idea of drawing the circuit for the summation in another way. This new way consists in dividing the addition process in 3 steps corresponding to each of these equations. First step, second step, third step. In the first step, from A and B, we get G and P. In the second step, from G and P, using the combined equation, we get C. And with C and P taken from here, in the third step, we get the sum, because the sum in a full adder is always the exclusive OR gate of A, B, and C. Let's see then what is the relative importance of the carry generate and propagate process when compared to the ripple hand process. In the rippling process, the n bits of A and B are all available at the start, at time 0. Also, from the start, each full adder block is ready to operate, but to complete the sum has to wait for its corresponding input carry to come. So, in the ripple adder, the carry propagation is more critical than the sum. The maximum arrival time goes obviously all the way through the carry's propagation until the sum of last bit. Consequently, the critical path is the carry's propagation transfer. So, this is why in the rippling adder it is more important the carry propagation than the sum generation. The sum can take extra time to generate, but the carry has to go faster because it has to propagate to the last stage. In summary, in a circuit of an adder, we have to prioritize the carry propagation circuit over the sum generation circuit, because the delay of an adder depends of n-1 times the carry, but only 1 times the sum. Conversely, in the second diagram, by calculating the propagate function and the generate function in parallel and using it as an intermediate step, we can then generate the carries in advance. So, what are the advantages of this propagate and generate strategy? First, with this strategy, all the carries are generated in advance by the equations, and knowing the digits A and B of each column, we can calculate all the sums in one shot. And second, The overall sum delay does not depend on the number of carries, whereas in the rippling diagram, the total delay depends on the numbers of carries. So, in conclusion, to optimize the design of an adder, a helpful idea is to search for patterns in the calculations from which to find out repetitive scenarios that can be transformed into equations. These equations are then used to design the new process. In this effort, it may be acceptable to use intermediate steps that delay or lengthen the path towards the sum generation, if by doing this we can speed up the carries propagation by generating them in advance. In any case, to effectively speed up the result, the carries propagation function must be fast. These conclusions may help us in our quest to find improved adder circuit designs. In fact, this is the idea behind the design approach of the carry look-ahead adder circuit that we will explain in the next video. Thank you very much for your attention. Have a nice day. If you like this video, please hit the like button and subscribe for more videos.